At the end of this video, you should be able to explain the difference between mass and weight, and find the direction and magnitude of normal forces. Chapter 4, Section 4, Everyday Forces. Weight. How do you know that a bowling ball weighs more than a tennis ball? If you imagine holding one ball in each hand, you can imagine the downward forces acting on your hands. Because the bowling ball has more mass than the tennis ball does, gravitational force pulls more strongly on the bowling ball. Thus, the bowling ball pushes your hand down with more force than the tennis ball does. The gravitational force exerted on the ball by Earth, represented as F sub g, is a vector quantity directed toward the center of Earth. The magnitude of this force, F sub g, is a scalar quantity called weight. The weight of an object can be calculated by using the equation F sub g is equal to ma sub g, where a sub g is the magnitude of the acceleration due to gravity, or free fall acceleration. On the surface of Earth, a sub g is equal to g, and F sub g is equal to mg. In this course, g is equal to 9.81 meters per second squared, unless otherwise specified. Weight, unlike mass, is not an inherent property of an object. Because it is equal to the magnitude of the force due to gravity, weight depends on location. For example, if the astronaut on the screen here weighs 800 newtons, which is about 180 pounds, on Earth, it would weigh only about 130 newtons, which is about 30 pounds, on the Moon. The value of a sub g on the surface of a planet depends on the planet's mass and radius. On the Moon, a sub g is about 1.6 meters per second squared, much smaller than 9.81 meters per second squared. Even on Earth, an object's weight may vary with location. Objects weigh less at higher altitudes than they do at sea level, because the value of a sub g decreases as distance from the surface of Earth increases. The value of a sub g also varies slightly with changes in latitude.
The mass of an object depends on the amount of matter the object contains. As long as the amount of matter remains constant, so does the mass of the object. The weight of an object depends on the force gravity exerts on it. Therefore, if the force of gravity on an object changes, so does its weight. The weight of an object depends on gravity. Changing an object's location will change its weight. For example, consider an astronaut who has a mass of 80 kilograms. On Earth, this astronaut weighs 784 newtons, but on the Moon's surface, where the force of gravity is only 1.6 meters per second squared, the astronaut weighs 131 newtons. The astronaut's mass, however, remains the same on Earth or the Moon. Weight can be measured using a spring scale. The spring scale measures the force exerted on an object by gravity. The weight of an object is expressed in newtons. Mass is measured using a balance. A balance uses a comparative mass on a lever arm to determine the mass of an object. The mass of an object is expressed in kilograms.
The normal force. Imagine a television set at rest on a table. We know that the gravitational force is acting on the television. How can we use Newton's laws to explain why the television does not continue to fall toward the center of Earth? An analysis of the forces acting on the television will reveal the forces as they are in equilibrium. First, we know that the gravitational force of Earth, F sub g, is acting downward. Because the television is in equilibrium, we know that another force, equal to the magnitude of F sub g, but in the opposite direction, must be acting on it. This force is the force exerted on the television by the table. This force is called the normal force, represented F sub n. The word normal is used because the direction of the contact force is perpendicular to the table surface, and one meaning of the word normal is perpendicular. The image on the screen now shows the forces acting on the television. The normal force is always perpendicular to the contact surface, but is not always opposite in direction to the force due to gravity. The diagram on the screen here shows a free body diagram of a refrigerator on a loading ramp. The normal force is perpendicular to the ramp, not directly opposite the force due to gravity. In the absence of other forces, the normal force, again F sub n, is equal and opposite to the component of F sub g that is perpendicular to the contact surface. The magnitude of the normal force can be calculated as F sub n is equal to mg cosine theta. The angle theta is the angle between the normal force and a vertical line, and is also the angle between the contact surface and a horizontal line.
When talking about forces, the word normal means perpendicular, and it always indicates the direction that is perpendicular to the surface of contact between two objects. Consider an object resting on a flat surface. The external force of gravity is acting on the object. The object is not moving down, so there must be another external force acting on it. This is the reaction force of the surface on the object. In this case, the normal force is exactly opposite to the force of gravity, but as the inclination of the surface of contact changes with respect to the ground, the normal force is no longer in the exact opposite direction of the force of gravity.
At this point, you should be able to explain the difference between mass and weight, and find the direction and magnitude of normal forces.